Our project was to create artificially generated slow motion videos. We do this by interpolating artificially generated frames in between the real frames to give it a smooth slow motion effect. In this demonstration, we are running our interpolation without our neural network because our neural network is still in training on GPUs. The neural network will smooth our results out, but we still have some pretty impressive footage to share with you. And here's how it is.
All right, hello guys. We're gonna show you guys the GUI of our project. It is built on C++. It's built with C++ with a Win32 API and Windows 10 SDK, as well as some of the C++ builder tools. So first thing we're gonna do is we're gonna open a video to slow down. We just select a Y4M video. We're gonna open it. And this will pop up once we're done processing the video itself. And we're going to slow it down by 4 times. And then there is a terminal here that will show us the process or the progress that this generation is taking. And it's going to take a while. But we'll catch you guys later after the break of the before. And then after. This is obviously 4 times slower. And yeah, that's pretty much it. I mean, you can even see this is about 12 seconds, and then this one's gonna be about 48. Yeah, 48 seconds. So that's it, guys. Thank you.
Optical flow vectors refer to the vector field between two images, describing how to move the pixels in one image to create the second image. We take advantage of the NVIDIA Optical Flow SDK to generate these flow vectors at a much faster rate than traditional deep learning methods. Although the application should simply take the flow vectors between adjacent frames, for training purposes we needed to take the flow vectors between frames that were far apart. Additionally, we needed to get the flow vectors in both directions, forward and backward vector flow. Thankfully, the Optical Flow SDK provides support to do both these things.
So after the NVIDIA SDK generates the flow files and we extract all the YUV frames, we have to map those data files to tensors for our network. The YUV files are in YUV 420 planar format, so we need to upsample the color values. Each U and each V value are upsampled to 4 different Y values to map to a tensor that has 3 color channels. After we've mapped the YUVs to tensors, we have to transform them to RGB space because our model is trained on RGB space. And then eventually we need to reconstruct them back to YUV files. So the image on the far left is the input YUV, the image in the middle is the intermediate RGB, and the image on the far right is the output YUV. The images on the left and the far right have very small differences because there is some data loss that occurs during these transformations.
This graphic shows the inputs and outputs of our interpolation step. To interpolate an arbitrary number of intermediate frames, it is intuitive to move each pixel value from frame I0 towards I1 along the flow between them, which is F0 to 1. However, this might leave holes in the resulting image. Therefore, we referenced existing literature in the computer vision space and opted to use backward warping to ensure that each pixel is filled. You can see in the graphic above that this allows the warped intermediate frame to guarantee having a value at each pixel position. In order to do this, we estimate intermediate flows at t time using the equations in the first box. It is important to note that using backward flow along with forward flow helps mitigate mistakes and occlusions in the images. Then, we apply a grid-based backward warping function on the frames and flows to produce warped images that are summed using the third equation for the resulting intermediate frame. This approach produces good results in locally smooth regions and during linear motion while maintaining good runtime efficiency. To improve our results further, we offer our client an additional solution to smooth the results. We employ a U-Net convolutional neural network model proposed by researchers at Northeastern University that we trained with our own methods. Its purpose is to smooth intermediate flow that can again be used to warp the images, as well as predict visibility maps that have the dedicated ability to handle occluded pixels.